So the last little topic of Unit 2 has solubility and pH. Now next unit, Unit 3, is all about acid-base. So we'll get way more into pH. But today I'm just going to kind of go over basics of pH if you don't already know them and talk about how solubility is affected by them, okay? So first we need to talk a little bit about water. Water ionizes. What will happen is that you'll get what's actually happening is that two water molecules will crash into each other, and then the H from one will go to the other. So you'll end up with H3O plus and OH minus. And this happens to a very small degree, but it does happen. So you can write it this way, your two H2Os that collide, or you can just write it this way and pretend that water decomposes. H2O at equilibrium with H plus and OH minus, okay? But it does happen. When that happens, it's in equilibrium, so it doesn't matter which way you write it, you're going to have an equilibrium arrow, okay? And our KEQ would be H plus over OH times OH minus over 1 because H2O is liquid, right? So because H2O is liquid, it doesn't factor into our expression. Remember, that's only soluble solutions and gases, aqueous and gases. So you can write it like this, or you can write it using this one. Same deal because H plus and H3O plus are the same. This equilibrium is K, but it has a special letter. It's KW. Okay, and we're going to use KW a lot, and W stands for water. So we're going to use KW a lot in the next unit. So in pure water, H plus is equal to the OH minus concentration, and that concentration is 1 times 10 to the negative 7. Okay, so Kw, if you plug this in for H plus and you plug this in for OH minus, Kw is equal to 1 times 10 to the negative 14. And that's the magic number that we'll be talking about quite a bit. That's Kw. So, and then there's this bit about water. Are you drinking acid and base? Kind of, but not really. Because they're equal to each other, we consider them neutral, okay? Because H plus and OH minus are equal to each other. What's interesting here and what we can actually use this for is that Kw is true not just for pure water, but for any aqueous solutions, because aqueous solutions have water in there. Okay, so Kw can be used for any aqueous solution, and that helps us with pH. In most aqueous solutions, H plus and OH minus are in small quantities, and we would be writing out such small numbers. We're going to convert these numbers to 10 logs. That's your pH. Okay, we're very familiar with pH. This is kind of where it comes from. So pH, the pH formula that we will certainly be using is right here. So when you have your H plus concentration, you take the negative log of it and you get your pH. So an example, in pure water, H plus, we just said, is 1 times 10 to the negative 7. So if we take the negative log of this, we get a pH of 7. And that's something that everyone kind of is familiar with. Water has a pH of 7. If your H plus concentration is higher, so here we went up higher quite a bit, from 1 times 10 to the negative 7 to 1 times 10 to the negative 4. When you pH that, or P that, you get 4. So P is like a mathematical application. You can really find the P of anything, and you just do negative log. So we tend to stick to pH and pOH. Okay, we're going to use pOH is just when you take the negative log of the OH concentration, and that's something that we might have and we might use quite a bit. What's nice is that they are super related. Okay, so because we know Kw, like for example, that H plus one that we just did, when the H plus was 1 times 10 to the negative 4, since we can use this formula here, plug in the H plus here, plug in Kw, and we know that OH would come out to be 1 times 10 to the negative 10, and POH would then be 10. You take the negative log of that. Okay? So you might notice something here, but if you don't, you can take a look at this chart. And this one tells you the pH and POH of some different substances. And if you look at all of them, you can see they all add up to 14. And that's true. If you have the pH of any substance, you can take 14 minus that and get the POH, and vice versa. If you have the POH, you take 14 minus that and you get the pH. And that's something that's very helpful for us because sometimes we only know one concentration or can only find that one concentration. And this is just saying if you have pH, you can calculate the H plus, then you can use Kw to calculate the OH minus, and then the POH. So this little pH scale or pH cycle we can go through. All right, so let's take a look at a type of problem that would be given. So the pH of a saturated zinc hydroxide solution, which was just, we didn't precipitate anything, so we don't have to worry about that stuff we were talking about in the last video. We just took zinc hydroxide and put it in water, is 8.75. Calculate the KSP. So let's draw, or write, that's not really drawing. Our reaction and our KSP expression. Okay, so we have the pH. If the pH is equal to 8.75, whoops, that means the POH is equal to 14 minus 8.75, which is equal to 5.25. We also know that the POH is equal to the negative log of the hydroxide concentration. So if you want to solve for, if you have the POH, and you know that's negative log of OH minus, you can find the OH minus concentration by taking 10 and raising that to the negative 5.25. Okay, that's how you would solve this little expression here. So the opposite of negative log is taking 10 to the negative of that number. So when you do that, you get an OH minus concentration of 5.6 times 10 to the negative 6. That number can go right in there. Zn, if we look up here, we know this is going to be 2s and this would be s right here. So we know for our Zn concentration, we should just divide this by 2. That can go right there. So for our KSP, we're going to plug in 2.8 times 10 to the negative 6 times 5.6 times 10 to the negative 6 squared. And that gives us a KSP of 8.9 times 10 to the negative 17. So same basic idea, we're just now using our pH number to figure out what our concentrations of OH minus, etc. are, okay? So it's just another way to do the same type of problem. So same basic idea. for this one. They give you the KSP. Oh, this is like an old problem that we've done. This doesn't have pH. We're going to go on to pH problem with it. Okay. So for right now, this is just like an old problem we would have done. Magnesium hydroxide gives you magnesium 2 plus 2OH minus. So we know this would be minus S plus 2S. KSP is Mg 2 plus times OH minus squared. So this is just a regular KSP problem that you would have done at the beginning of this topic. So your KSP is 4S cubed. S, which is equal to the Mg2 plus concentration, is this. And then 2S, which is equal to the OH minus concentration, is just 2 times that. So that's just a basic KSP problem, but if we go to the next slide, what would the pH be of 200 milliliters of this saturated solution? So same deal, calculate each ion, that's the same question. Now we're going to find pH. So on our last one, we found that the concentration of OH was this. So the pOH would be the negative log of that. So that comes out to this. To find pH, you just take 14 minus that. So your pH is going to be 10.18. Okay, so now this is just adding something else onto this question. So the first part we've already done. Now let's calculate the mass of magnesium hydroxide, which would be dissolved in a liter of this saturated solution. So we know that the Mg2 plus equals S, which equals the amount of MgOH2 that dissolves. The reason I'm not using OH minus is just because that was 2S, so we might as well just use S. We've already done that. Okay? To figure out the mass, what they're saying here, if it's grams in a liter solution, it's just what we have done before, finding the gram solubility. So to find the gram solubility, you take the moles per liter. So this is just a nice little review. And then for 1 mole, our molar mass, 58.33 grams. And so your gram solubility, the amount of magnesium hydroxide that would be dissolved in 1 liter, is this. All right, so now this is asking you to find the pH of a saturated solution of nickel 2 hydroxide. We give KSP. So our nickel 2 hydroxide so this is a 4S cubed problem. Our KSP is equal to nickel times OH squared. So we know that's going to be 6.0 times 10 to the negative 16 is equal to 4S cubed. So then we have S is equal to this. So 2s, because we know for OH is going to be 2s, is equal to 2 times that. So that's the concentration of OH minus. You can go ahead and find the P of that, POH, negative log, which is 4.96, and then to find the pH, you just subtract that from 14. So pH is 9.04. Here's a little bit about significant figures with pH. Okay, there's nothing much to do here with this one. In the previous problem, KSP has 2 sig figs, but why does the pH look like it's 3? So if you take a look at these, you can see that whatever this number is, where the sig figs come from, that affects only the stuff after the decimal point. Okay, so that's what we do our sig figs based on. So the stuff before the decimal point for pH doesn't count for significant figures. So that's why they look kind of funny, but if we have 2 decimal places, that's 2 sig figs for pH. Okay, so this question says, calculate the molar solubility of nickel 2 hydroxide in a solution with a pH of 9.7. What this is code for, AP code, is find out how much nickel 2 hydroxide can dissolve when there's already OH minus present, right? Because if we know that the pH is this, we know there's some OH minus, so it's a common ion problem. It's just a common ion problem with a little twist. You have to find the hydroxide concentration first. So for pH, we're going to find POH first. So that's going to be 4.30. Then we can do our 10 to the negative POH. So if you have POH, if you have the OH concentration, you're going to take 10 to the negative POH to find it. So 10 to the negative 4.3 equals 5.01 times 10 to the negative 5. So now we can plug that into our KSP expression and look for the solubility. Okay, so it says molar solubility, so that's nice. We don't have to do any conversions. We know KSP will be this. And then we can just put S here for a nickel. And that's going to be our molar solubility because it's nickel and nickel 2 hydroxide have a 1-to-1 ratio. So then your molar solubility comes out to 2.39 times 10 to the negative 7 molar. Last little bit that you might see, do you think this is more or less soluble than it would be in water? Common sense, I think, with a common ion problem, we kind of already know it's going to be less soluble, but if you want, you can go ahead and do that out. If it was just a regular solubility problem, you would set the KSP equal to this. And if there's no common ion, if it's just in regular water, all of this, it's going to be S and then 2S. So we're going to get 4S cubed, and S would be equal to this. Okay, so we know that this -6 10 to the negative 6 is going to be higher than 10 to the negative 7. So it is more soluble in regular water than it would be in our pH of 9.7.